We know that plane mirrors form virtual images. A virtual image is an image which seems to be formed behind the mirror, but in reality, it isn't formed there. To find the location of this virtual image behind the mirror, we use ray diagrams. Yes, we draw ray diagrams on a paper to find the locations of images. Now it might sound odd to you to find the location of something which is only in our mind and not actually there. But what we can say is that a perceptual location of the images using ray diagrams helps us to understand and verify the properties or characteristics of these images. In our previous video, we have already seen few of these properties. Okay, so how do we draw a ray diagram on a piece of paper? Let's first try to draw a ray diagram for a point object. Drawing a ray diagram for a point object is very easy. Okay, so I want you to find the location of the image of this point object on the other side of the mirror. To do that, we need rays of light emerging from the point object. For a point object, we need only two rays. So let's draw two rays emerging from this point object and incident on the mirror. Now at this stage, I want to mention that any two rays will suffice. For instance, instead of these two, we can take these two or even these two. Any two incident rays will work. These rays will be reflected by this smooth surface of the mirror. So we will also draw the reflected rays. Are the rays obeying the laws of reflection? Yes, this is very important. Whenever we are drawing ray diagrams, we should make sure that all the rays of light which are incident on the mirror must obey the laws of reflection. Hence, take help of a protractor to verify that the angle of incidence is equal to the angle of reflection. We see that in this case, laws of reflection are indeed being followed. If you notice in this case, the reflected ray is coincident with the incident ray. This is because here the incident ray is incident perpendicular to the mirror. So it will be reflected in opposite direction. Okay, now we extend the two reflected rays backwards and the point where they meet behind the mirror is the location of the image. Yes, the image of the point object seems to be formed at this point. Now suppose the point object was at this point instead of this. Can you find the location of the image now? Pause the video and give it a try. Again, we draw any two rays emerging from this point which are incident on the mirror. We draw reflected rays making sure that the laws of reflection are obeyed. Extending both the reflected rays backward will give us the location of the image. So if we look at the image at this point object, it will appear as if the image is formed here. But wait, there's something interesting here. Measure the distance between the object and the mirror and the distance between the image and the mirror. We notice that both are the same. This verifies one of the characteristics of images that we saw in our previous video. What if it's not a point object? This is a picture that we saw at the start of the video. Can we find the location of this object behind the mirror? Notice that this is not a point object. So let's replace this object with an arrow. This upward arrow represents our object under consideration. Don't confuse it with a ray of light. To avoid confusion, I will darken this arrow a bit. This is our plane mirror. Let's now try to determine the location of the image of this arrow. How do we do that? Well, you can think of this arrow as containing infinite points. So we can take any random number of points on the arrow and find out the location of images of those points first. For an arrow, 2 points will suffice. Let's take these two extreme ones. Again, we follow the same procedure and find out the location of the image of each point. Yes, we get these two images of these 2 points. Next, we join these 2 points and we get the image of our arrow. We would have got the same result if we would have taken 2 different points. Their image would definitely be formed on this arrow only. The image is virtual and erect. Measure the length of the arrow and its image and you will find that both are equal. Also, both are at equal distance from the mirror. So we got the required location of the image of our object. This is where it appears to be present. Now, ray diagrams not only determine the location of the image of an object, but also tells us the path that the light follows when we are looking at some point on the image. For example, suppose that we're looking at the top of the image from here. To us, the light rays seem to come from here, but in reality, no light ray is reaching us here. From our previous videos, we know that we're able to see the image because the light rays from the object are getting reflected from the surface of the mirror. And these reflected rays travel to our eyes. So here as well, these are the reflected rays traveling to our eyes. But where is the incident ray? How can we draw incident rays for these reflected rays? We can use laws of reflection to do that. We draw a normal measure angle of reflection. We draw incident ray on the other side of the normal, making the same angle with the normal. So this is a ray diagram which represents the path of light when we are looking at the top of the image. What if we are looking at the bottom of the image? Can you draw a ray diagram representing the path of light in that case? I will leave that for you. In the next video, we will talk about spherical mirrors. And I'll see you there.